Well, hello, Honors Physics. It's been a while. Hope you're all still out there. This is going to be the last video thing for Chapter 13. So this is video 5 for Chapter 13. We are starting on page 360. Some of you may notice when you try to open up this page in your book that the pages are blank. I'm not sure why that happened, but just wait for a while. The pages are there. It just takes it a while for it to load. Must be a memory issue with the iPad or something, not sure, but mine did it too. So just be patient, wait it out. The pages will show up, okay? All right. So anyways, today's lesson is on thermal expansion. So today's lesson is thermal expansion. The idea behind thermal expansion is pretty straightforward. It's just simply that if you add heat to something, if you change the temperature of something, change the internal energy of something, lots of ways of saying it, that something will not only increase in temperature, its internal energy not only increases when you add that heat, as it turns out, the object will actually get bigger. Okay, it's called thermal expansion. Solids do it, liquids do it, gases do it. Things get bigger when you heat them up. Okay? So let's look at this. There's going to be two types of thermal expansion we're going to want to look at. There's going to be the one-dimensional case, things getting longer and shorter, and then there's going to be the volume case, things getting bigger in all three dimensions or things shrinking in all three dimensions. All right, so let's have a look at the one-dimensional case. So imagine, let's just look at some object. Let's try to draw here. So we got some object. This is just some chunk of something. And we're going to say for right now that chunk of something has some initial length. So there's my initial length, Li. And we're going to say this something is going to be at some initial temperature. So it's at some temperature. So we have some chunk of something, it's some length, and it's at some temperature. Okay, not to be overly specific here. Okay, the idea is that if I increase the temperature, the size of this object will increase. See if I can draw this getting bigger. All right, so we've now changed that size by delta L. The object is now a changed length. It is now bigger by some amount. Its length has changed. It has increased by the amount of delta L. Okay, and this new part is going to be at our final temperature. The new thing's at its final temperature. So how do we determine how much the length of an object changes? Actually, before I say that, let me go back and remind you. Delta L is like any other delta. It's just final minus initial. And delta T, just like any other delta, is just final minus initial. So just to remind you of those things. All right. What is the change in length here? Well, the amount that the length is going to change is going to depend on a few things. It's going to depend, one, on the material that we're talking about. Is this a piece of aluminum? Is this a piece of concrete? Is this a piece of lumber, a piece of wood? Who knows? The Greek letter alpha, we're going to call the coefficient of linear expansion. The coefficient of linear expansion. And if you go to your textbook on page 361, you'll see at the bottom, table 13.2, and you'll see in the middle column the coefficient of linear expansion, alpha, fish, for many objects. Aluminum, 25 times 10 to the minus 6. Glass, 9 times 10 to the minus 6, etc. Okay? So that is alpha. Alpha depends on the material itself, and it is just the way, it just describes the way in which the material responds to having heat applied and how it's going to change in size. Okay? So we have alpha. The Greek letter alpha represents the material that we're talking about. The next thing that's going to change, that's going to affect how much this thing expands, is the initial length. Every piece of the object expands. So if you have a small object, then there's a small number of pieces that are expanding, so you get a small amount of expansion. If you have a very large object, then there's a very large number of pieces, and each one of those large number of pieces will expand a little bit, so there's going to be a whole bunch of little expansions, so you get a much bigger expansion. So because all of the object expands, the more of it there is, the more there is to expand, so the more it can expand. Okay? So the amount this is going to increase in length depends on the initial length. This is also going to depend on the amount that we change the temperature. So it's going to depend on, if I could draw a delta, it's going to depend on the change in temperature. So if I change the temperature a little bit, the thing's not going to expand very much. If I change the temperature a whole bunch, the thing expands. Now keep in mind, if the thing's a solid, we talk about changing its temperature and expanding it, but if you change its temperature too much, you actually start to melt it, and that's not what we're talking about here. We're not talking about change in state, okay? So we're talking about changes in temperature that don't actually result in melting and boiling and freezing and all that sort of stuff, okay? So there you have it. You have the coefficient of linear expansion and the role it plays in linear expansion, delta L. And just to remind you, just in case it's not obvious, delta L is L final minus an L initial. That'd be alpha. And then T is just going to be T final minus T initial, in case that wasn't obvious. All right. The next thing to do is to look at the same exact problem, but instead of talking about changing the length of something, instead of talking about a one-dimensional increase, let's talk about volume increase. It works exactly the same way. So we're going to have some change in volume. That's going to be equal to a coefficient, except instead of alpha, because we're talking three-dimensionally, we'll use a different variable. That's the Greek letter beta. Beta is going to be the coefficient of volume expansion. And if you look on page 361, table 13.2, you'll see the last column shows you the coefficient of volume. So for aluminum, the coefficient of volume, beta, is 75 times 10 to the minus 6. If you look closely, you'll notice that beta is always 3 times alpha. For aluminum, we have beta is 75, aluminum alpha is 25. That's 3 times different. So just as a little side note, it's handy to remember that beta is just 3 alpha. Okay? Anyway, so we have the coefficient, the thing that is determined by the materials. You have the initial volume, same logic as with the initial size, right? The more of it there is, the more it can expand, and the change in temperature. So, and just like before, you could say that's just going to be V final minus V initial is going to be beta V initial times T final minus T initial, if you want to see it that way too. But the simplest form of the equation is just this form, and the simplest form of the other equation is this one. Those are the two simplest forms. But the other ones, if you can't see the algebra. Okay? So, coefficients of linear and volume expansion and how they relate to the actual change in length or volume of some material when that material's temperature has been changed. Let's try a problem. Let's try the problem on page 362. Example problem 4, page 362. Example problem 4 says, a metal bar is 1.6 meters long at room temperature 21 degrees. The bar is put into an oven and heated to a temperature of 84 degrees. It is then measured and found to be 1.7 millimeters longer. They want us to determine the coefficient of linear expansion. In other words, they want us to determine alpha. All right, so let's see what we got. We have an initial length of 1.6 meters. We have an initial temperature of 21 degrees. We have a final temperature of 84 degrees. And we were told that the length changed by 1.7 millimeters, so 0.0017 meters. Notice our subtle change of units. Don't forget. And they want us to calculate alpha. Alrighty? Well, let's see. Delta L is going to be alpha L initial delta T. So alpha is going to be delta L divided by the initial length times the change in temperature, which would be T final minus T initial. All right, let's plug in our numbers. Alpha is going to equal the change in length, 0.0017 meters, divided by the initial length, 1.6 meters, times the change in temperature, which is going to be 84 minus 21. That gives us a value for alpha of 1.7 times 10 to the minus 5. Yay! All right, hopefully that made some sort of sense. What I would like you guys to do now is, on page 362, work on numbers 39, 40, and 41. Give those a try. Those will be practice for you. Once you've done those practices, just start getting onto your homework. If you see Shobi, you'll see that there's a folder created to get your homework turned into. As a quick hint, number 39 is asking you to calculate delta L. Number 40 is asking you to calculate the final length. And number 41 is asking you to calculate the change in volume. Hopefully all that makes sense, and hopefully you're still out there. And I'm going to end this